Alright, so today we're going to talk about chapter 3.2, which is all about gas laws. And buckle up, because this one's going to be a little bit of math, and it's going to be a little long, and you might not understand it the first time around, but that's okay, because we are going to do tons of work on this stuff in class. So now that we know what gases are, specifically they're particles with a high kinetic energy zooming all around that have variable volume and shape, we've got to learn some properties about gases. And the first really important property of gases is pressure. And pressure is the result of a force distributed over an area. So if you're in the hallway and you're leaning on your locker, the force that you're pushing on your locker with isn't just concentrated in one tiny little area. It's concentrated over the entire area that you're applying. So if you're leaning on it with your hand, the force of you leaning is distributed over the entire area of your hand. And that's a pressure. And pressure is measured in the units of pascals, which is abbreviated PA. Gas pressure specifically is caused by collisions between the particles of the gas and the walls of the container. So as gas particles zoom all around, they hit the sides of the container, applying forces. And those forces are applied along the entire surface area of whatever container they're in. And because it's a force distributed over an area, it's a pressure. So when you blow up a balloon, the pressure inside that balloon is caused by the particles inside the balloon zooming all around and hitting the walls of that balloon. And that's what causes it to stay inflated. So there are factors that affect the pressure of an enclosed gas, and these are temperature, volume, and the number of particles. So temperature. It turns out if you raise the temperature of a gas, you will increase the pressure if the volume and the number of particles are constant. And this kind of makes sense because the warmer particles are, the faster they move, causing them to bump into the walls of the container much more often and with more force. So an example of this is a balloon. If you ever go outside in the middle of winter with a balloon, it shrinks and it gets smaller. And that's because the temperature of the gas has decreased, meaning the particles are moving much more slowly than they were before. They're not hitting the sides of the balloon as much as they were before or as strong as they were before. And that causes the pressure to decrease, which is why it shrinks a little bit. Volume, on the other hand, if you reduce the volume in a container, that will increase the pressure inside the container. And this kind of makes sense too, because if the walls of a container are closer to each other than they were before, that means the space the particles have to zoom around in is much smaller, and they're going to hit the sides of the container much more often. This happens if you take a balloon and you squish it. If you squish it, you're decreasing the space that the volume takes up. You're decreasing the space the balloon takes up, you're decreasing the volume. And the particles inside that balloon are going to hit the sides of the balloon much, much more often than they were before. This is why if you squish a balloon too much, it pops, because the pressure will increase and increase and increase until the balloon can't withstand it anymore. And finally, the number of particles. This one's kind of a no-brainer, but if you increase the number of particles, that means the pressure will increase. And this makes sense because the more particles you have in there, the more particles you have to collide with the walls, and the more pressure you'll have. This is like trying to blow inside a 2-liter soda bottle. If you keep blowing and blowing and blowing air in there, you're putting more and more and more particles in, and eventually it's going to be really hard to push more air in because the pressure is going to be a lot, and your lungs won't be able to add even more pressure. Now, it's kind of cool, and there are some equations that actually tell us how these concepts relate to each other. And I think it's cool because it's really neat that the laws of nature and the way that the universe works can actually be summed up by math at times. So today we're going to learn about 3 equations: Charles's law, Boyle's law, and the combined gas law. And these laws, these equations, tell us how pressure, volume, or temperature of a gas all affect each other. So Charles's law is the relationship between the volume and the temperature in a gas. And the equation itself is V1 divided by T1 equals V2 divided by T2. Now, an important note, the 1 and the 2 here don't mean gas 1 and gas 2. They mean gas before a change and gas after a change. So this is like if I have a balloon and I take the volume and the temperature, and then I have that same balloon and I increase the temperature. It's the same gas, I've just had it undergo a change. Now what this means in words, which some of you might have a hard time interpreting, is that if the temperature increases, so does the volume, if the other things are constant. Or the other way around, if the volume increases, so does the temperature. So that means if one goes up, the other goes up. We call this directly proportional. And there's a note to this one. Temperature must be measured in Kelvin. I'm sure you've heard of the Kelvin scale before, but we'll talk about it more in class. It is the most accurate scientific unit we have for temperature. So with all of these equations, we are going to use Kelvin. So V1 divided by T1 equals V2 divided by T2. That's Charles's law. The next one is Boyle's law. And Boyle's law is the relationship between pressure and volume. And this one is a little bit easier to remember because there's no division. It's just P1 times V1 equals P2 times V2. And what this means in words is that as the volume increases in a container, the pressure of the gas decreases. So if I have a container and I make it larger, I increase the volume, the pressure inside that container will decrease because the particles are not hitting the walls as much as they were before. And finally, the craziest equation that we have is called the combined gas law. And the combined gas law, let's see, my thing isn't working. All right. The combined gas law tells us the relationship between pressure, volume, and temperature. So all three of these things. And the equation is written P1 times V1 divided by T1 equals P2 times V2 divided by T2. So it's like we have Boyle's law up top, and we have Charles's law in between on both sides. So it's kind of a combination of both Charles's law and Boyle's law, which is why we call it the combined gas law. And let's do a sample problem together just so you can see how you would interpret a problem and to figure out which equation to use. So the question is, a cylinder that contains air at a pressure of 100 kilopascals has a volume of 0.75 liters. The pressure is then increased to 300 kilopascals. The temperature does not change. Find the new volume of air. So the first thing I'm going to do is pull some information from this problem. I know that my beginning pressure, P1, is 100 kilopascals. I know that my beginning volume, V1, is 0.75 liters. I know that my second pressure, the pressure after I make a change, is 300 kilopascals. And I'm trying to find the new volume, which is going to be V2. And I know that T is constant. Now this is a really, really important point. T is constant. What that tells us is we want an equation that does not have T in it. We don't care about T. It is exactly the same before and after, so we can completely ignore it. So let's go back and look at our three equations. The first one is Charles's law. Charles's law includes volume, but it doesn't say anything about pressure, which is a lot of the information we have, and it includes temperature, so we don't want that one. The second one is the combined gas law, which includes all three things, which is great because it tells us about pressure and volume, but it also has temperature in there, which is just going to complicate things. So we're not going to use that one. So the equation we want to use here is Boyle's law. It has information about pressure and volume and nothing about temperature. So this is the equation that we want to use. So if I make myself a little bit more space here, we want to use Boyle's law. So P1V1 equals P2V2. And now it's just a matter of plugging in the numbers. P1 is 100. P2 is 300. P3 is 300. P4 is 300. P5 is 300. P6 is 300. P7 is 300. P8 is 300. P9 is 300. P10 is 300. P11 is 300. P12 is 300. P13 is 300. P14 is 300. P15 is 300. P16 is 300. P17 is 300. P18 is 300. P19 is 300. P20 is 300. P21 is 300. P22 is 300. P23 is 300. P24 is 300. P25 is 300. P26 is 300. P27 is 300. P28 is 300. P29 is 300. P30 is 300. P31 is 300. P32 is 300. P33 is 300. P34 is 300. P35 is 300. P36 is 300. P37 is 300. P38 is 300. P39 is 300. P40 is 300. P41 is 3 V1 is 0.75, P2 is 300, and V2 is what we're solving for. Now, I put a question mark over here for V2, but I'm not going to put that question mark in over here. And the reason I'm not going to do that is because if I were to just put a question mark in this place, I would have no idea what I was solving for. And when I was done with the problem, I wouldn't know what units to put, I wouldn't know what that number represented, so I'm going to leave it as V2 so that I know, looking at this equation, okay, I know all these things and I'm trying to solve for the second volume, the volume after the change. Now the first thing you want to do is figure out what this is on this side. We have 100 times 0.75, and if you plug that into a calculator, or you could do it in your head, you would see that that equals 75. So we have 75 equals 300 times V2. And in order to get V2 all by itself, which is what we want to do to solve, we have to divide both sides by 300. So I take 75, divide by 300, and when you put that into a calculator, it turns out you get 0.25 equals V2. Now, we're not quite done. There's one more step, and that's to put units. So we talked about how the units of volume are going to be cubic centimeters in our class. But when it comes to math problems, you really need to look at the information you're given in the problem. So if we go back to the problem, we say a cylinder that contains air at a pressure of 100 kPa has a volume of 0.75 liters. That's really important because whatever unit we start with for volume is the unit we need to end with for volume. So the unit we have here is liters. Now, like I said, this was a lot of information, it's a lot of math, and if you don't understand it the first or even the second or third time around, that's totally fine. We'll do lots of practice with this, and all I ask is that you guys have patience and work as hard as you can.